Today we're going to talk about the omnipresent Gauss integral. In my opinion, one of the most important integrals to know. The Gauss integral is defined by an integration from minus infinity to plus infinity of the function e to the power of minus x squared. We know that this integral is converging because e to the power of minus x squared is smaller than e to the power of minus absolute value of x, and we know that this integral is converging. So we know I equals a real number, and let me spoil you. This real number is square root pi, which is super surprising because this integral has no connection to pi or any circle. This once again shows why math is incredible, because we can connect the seemingly unrelated topics like this integral and pi and find a connection by their reasoning. Let's get into the details how we can find the solution. When we want to solve an integral, we normally try to find the antiderivative. But in this case, it is not possible because our function is very difficult and we do not manage to find an antiderivative. We cannot do it like that. Normally, if we cannot find the antiderivative directly, we use common methods like integration by parts or substitution. But in this case, we also don't find a solution with these techniques. I dare you to try so, but I can guarantee you, you will not find a solution with these techniques. We need more advanced techniques to solve this integral. To solve our tricky integral, I use the following ansatz. Instead of calculating I, I'm calculating I squared. So I noted it down here, and we can do a change of variables. X is an integration variable, so we can change it naturally. Knowing that e to the power of minus x squared is integrable, we can use Rubini theorem. Which allows us to do an integration over the whole plane r squared. From here on, we can do a change of coordinates, and we're going to switch from Cartesian coordinates to polar coordinates. A change to polar coordinates allows us to write our exponent x squared plus y squared as r squared. We can note our integral in the new coordinates, but while doing the transformation we also have to adjust the integration measure by the Jacobi determinant. For polar coordinates, the Jacobi determinant values are. We see that in this integral there's no phi dependence, so we can directly evaluate the phi integral and get a constant. To solve the remaining parts, we have to use a substitution. We define u as r squared. So this part becomes u. And to do a transformation, we also need a derivative. And this r is basically the derivative of u. We just need to add a factor. So this r equals 1/2 du dr. So we can now do our calculations. 2 pi. We also add the factor 1/2. our new integral over u this integral we can calculate very easily. So the antiderivative of e to the power of minus u is minus e to the power of minus u, and we have to put in the words plus infinity in 0, and we get 0 minus 1. So in fact we just get 1. So let's put it all together. So our final result is pi for I squared. So we just have to take the square root, and in the end we have our result. I equals square root pi. Amazing. To finish my discussion of the Gauss integral, I would like to give you some applications to underline the importance of the Gauss integral in mathematics and physics. My first example is the normal distribution in probability theory, and the normal distribution is undoubtedly the most important distribution in the whole of probability theory. Basically all measurements are normal distributed. Also in quantum mechanics, if we look at the harmonic oscillator in the ground state, we take a look at the wave function in the position space. It's also a Gaussian. Similar also in thermodynamics, if we look at the Maxwell-Boltzmann distribution of the velocity of an ideal gas, it is also a Gaussian. And if we want to have the probability of finding particles in a certain area of velocity, certain area of space, we have to do an integral over it. And that's why it's important to understand the integral intuitively. And I hope my video had helped to improve this intuition. Thanks for watching.